Welcome to this lecture number 27 of the course Computational Hydraulics. We are in module 2 numerical methods. In this particular unit number 23, we will be discussing tridiagonal matrix method. This comes under algebraic equations. Now, what is the learning objective for this particular unit? To apply tridiagonal matrix algorithm for direct solution of matrices. Specifically, we will be discussing a special kind of matrix, that is tridiagonal banded matrix for this particular lecture class. We have a basic form of tridiagonal matrix. In this case, tridiagonal structure, we have one diagonal term and two off diagonals. Off diagonals are adjacent ones. So, other terms are with 0 values. Now, if we have a large matrix, large n by n matrix, and we need to store this extra 0 values, where we know that if we multiply phi with that 0 value, obviously it will not add any value to our calculation process. So, what we can do, we can extend this up to one extra point, and on lower side also we will consider another point here. So, if it is a n by n total matrix, now we can divide this A matrix into 3 different column vectors. So, how this is possible? In diagonal term, we will have n values. So, let us say we have n cross n, one column vector, another one is for lower one. Although we know that this value is a dummy value, to keep the size consistent with the diagonal term, we will store this one extra value here, n cross n, n cross 1. So, what this is for maybe if we consider this for lower one, this is for middle one, and this is for upper one. So, let us say we are defining it with a diagonal term and below diagonal term and above diagonal term. And now, we need to store this phi and r as usual, because these are required for our calculation process. Only we will concentrate on the matrix A, and we will try to reduce the storage requirement for matrix A in this case. Now, like our Gauss elimination, we will have this 5 by 5 matrix, some example one. This is below term. So, essentially if we write this B1, B1 is 0. At the same time, if we consider A5, obviously A5 will be 0 in our calculation. But D1 to D5 will be there for our calculation process. So, phi these are as usual. Now, let us say that we are starting our calculation with row 1. Row 1 what is required? We have d1 phi 1, d1 multiplied with phi 1, a1 multiplied with phi 2 and r1 is there. So, with this if we write d1 phi 1 plus a1 phi 2 equals to r1, then we can straightway divide this this d1, this yields phi 1 plus a1 by d1, a1 by d1 and r1 by d1. These are some initial values, but interesting thing is that we are using the storage structure for B1 to B5, D1 to D5 and A1 to A5. So, in first case we can define it with a new variable, otherwise we can store A1, this equals to A1. So, A1 equals to A1 divided by D1 and R1 equals to R 1 divided by D1. Now, in this case rewriting we can see that if we define new variables xi1 and rho1, we can rewrite our first row. So, this thing we have changed. So, we have converted our diagonal term into unity and we have changed our off diagonal term. Obviously, we cannot change b, we have changed only a and rho. Now, in this case if we consider rho by multiplying B2 with rho 1. Now, remember that in Gauss elimination we have used unchanged or undisturbed rho 1 in our calculation process, but in this tridiagonal algorithm we are using same forward elimination, but we are multiplying this quantity with disturbed one because we have changed our first row. So, row 2 we are multiplying row 2 with B2, row 1 with B2 and again we can write B2 into phi 1, this is D2 phi 2 A2 phi 3 R2 and this is our B1 into row 1 B2 into row 1, this is B2 because diagonal term is 1. So, no coefficients are there. So, simply we are multiplying B2 and B2 into xi 1 this quantity is there as coefficient of phi 2 equals to B2 into row 1. Now, B2 into row 1 this is important term. Now, if we subtract this we can cancel this part. So, only thing that will be left is D2, B2 into xi 1, A2, R2 and B2 rho 1. Now, in this case, if we divide it by D2 minus B2, the D2 minus B2 into xi 1, and right hand side also with some quantity with the same quantity, we can get the transformed form of our rho 2. Our objective in this case is that to convert the diagonal term with a value of 1 as coefficient, and we are storing this thing. Now, please remember that whenever we are dividing any quantity, that D2 minus B2 xi 1, this should not be too small, otherwise this may create numerical error. If it is too close to 0 value, so it will introduce error within the system. Rewriting, if we write it in terms of xi 2 and rho 2, we can write the same thing, but in other form, but during implementation we are not going to utilize this xi or rho because our objective is to reduce the storage structure. So, we will utilize our A vector for storage of xi 2 directly, this quantity, and for R vector we can store this rho 2 value directly. So, similarly, if we reduce our rho 3, we can repeat the same thing here and we can reduce our rho 3. Obviously, you can see that unchanged coefficients are represented with blue color and changed coefficients or changed vectors are represented with red color here. So, up to rho 3 we have converted. Now, rho 4 and rho 5, the same process will convert this total thing into upper matrix. I will not say this is upper triangular because we are getting only diagonal term and upper or above diagonal term. So, now we can utilize this form for our backward substitution, because in the last row it is clear that the coefficient is 1, it is multiplied with phi 5 only, other coefficients are 0. So, obviously, this phi 5 equals to rho 5. Now, in this process we are starting from last row. So, last row if we start after first calculation we have got the value of phi 5. So, I have changed the color of phi 5. Now, in the next step rho 4 we will get the value of phi 4. So, step wise we are getting different values. Now, in this case there is no change in A and R vector. So, although this A matrix it is not a complete matrix, we have reduced it into diagonal and off diagonal level column vectors. We can utilize it directly for calculation. So, if we start with row and finally we will get this phi 1, phi 2, phi 3, phi 4 and phi 5 values. Now, we need to implement this in algorithm format. So, first what is input that is required? We need that below diagonal, this is diagonal and above diagonal vectors, and R is another right hand side vector. Now, the size of these vectors, this is n or 3n, 3n for B, D, A, and R is as usual you are utilizing this n for phi and n for R. These are column vectors n cross 1, n cross 1. So, 3n cross 1, that is required storage structure. So, instead of n into 1, n into our n, that means if we have n equals to 5, we need to store 25 elements of our A matrix, but instead of that we are storing only below diagonal, diagonal and above diagonal values or coefficient values in a column vector format. So, these are inputs. Now, output or result is phi. So, first is forward elimination, as I have told earlier that we are not utilizing xi and rho as our separate vectors, because that will require more storage. So, we are using A1 and R1 only. So, A1 equals to A1 divided by D1, R1 equals to R1 divided by D1. This means that in the first step, when we have converted this into xi 1 and this into rho 1, actually this is not required. We can store the same value in A, because A value is further not required for our calculation. In case of Gauss elimination, we have seen that we need undisturbed first level for our calculation process. Here it is not required. Now, we are starting from 2 to n minus 1. Why n minus 1? Because for nth row will have only our r term, because diagonal term will be 1. So, r term, and this is phi n. So, phi n equals to r n. So, in this process we are calculating up to our A I equals to A I divided by factor, that is for 2 to n minus 1. So, only for interior values, and at the end points we are explicitly calculating R n. We are avoiding the calculation of A n because A n is already 0 value. We already know because we have this kind of structure. So, lower value is 0. For B 1 this is not required. That is why in the first place we have calculated A 1, we already know that converted D 1 will be our 1. So, no need to write that value here, and backward substitution process we can directly write this as phi equals to R n because coefficient is 1. So, directly R n we can write because within R n only we are storing the values. Now, in this case one thing is clear, in Gauss elimination we have a 2-step process. We are fixing a particular row and then operating on other rows. In this case we are utilizing the information of the previous row and we are operating on the next row. So, only one loop is required, no 2 loops for this one. Similarly, for backward substitution this is clear because coefficients of phi this is 1. So, R 1 minus A 1. So, A 1 is storing the xi 1 2 values. So, this will give the actual value for this one because we need only phi I plus 1 value because we have only upper diagonal available, lower diagonal we have eliminated that and we have calculated it as 0 value. No need to utilize it within our calculation process. Now, in this case we can again utilize our standard example because this is having diagonal structure. So, in this case we can utilize the concept, this is not available, this first one is not available. Now, we already know what is the solution for this problem. We have utilized Gauss elimination and our LU decomposition for solution of this problem. Now, in this case we can use this tridiagonal matrix thing. This is comparatively a smaller code, it is not lengthy one. The CLC clear, these are basic lines that is required to clear the console and clear the memory in console. Then function required is phi, we need to supply B, D, A and R. This is TDMA solve. Now, n is the number of rows, n equals to length of D, D is the diagonal that we are transferring. Now, directly we are writing A 1 equals to A 1 divided by D 1, R 1 equals to R 1 divided by D 1. And in the forward elimination process we are calculating this factor I equals to 2 to n minus 1 because we do not need to calculate the A because nth value of A is not available. So, fact equals to d I minus b into a I minus 1. So, previous value, and with this factor we are just multiplying these to get a and r values, updated one, because diagonal will be automatically converted into 1 unity. In this case r n equals to r n minus b n, we are directly calculating this. Now, in backward substitution process, phi n equals to r n. Now, phi n equals to r n, that is similar to our Gauss elimination, but in Gauss elimination you need information about all previous variables, but in this case only the immediate previous variable, that is for phi I plus 1 is required, because we are moving in the backward direction. This is forward elimination, backward direction, we are starting from n. So, we already have n value here. Now, for n we are starting calculation of n minus 1. To calculate n minus 1 we need value of n. So, to calculate 1 we need value of 2, like that. So, finally, we can get the solution. So, now how to store, because in case of our LU and Gauss elimination you have seen that we have stored the matrix like this 1 0 0 0 0 1 2 1 0 0 0 1 3 minus 1 0, then 0 0 1 2 1 and 4 zeros and 1. This was the structure for A. Now, in this case we do not need to supply the matrix that way. So, we can directly supply this D. So, D is actually 1. So, we can eliminate these values, directly, and we can directly supply this 0. So, this is 1, this is 1, 1, 2, 3, 2, 1. So, this is 1, 2, 3, 2, 1. Next is below diagonal, this is B is 0, 1, 1, 1, 0. So, this is 0, 1, 1, 1, 0. Then above diagonal, this is starting from 0, 1, minus 1, 1 and last one is 0, and R, which is on the right hand side, this is 1, 12, 11, 28 and 9. Now, we can call this TDMA solver to get the solution. So, let us see what solution it is giving. Now, we can select it and evaluate selection. We can see that it is directly providing the desired solution. Desired solution is our 1, 3, 5, 7, 9 odd numbers. Now, we can see that with a minimum storage we are getting maximum output. So, a matrix structure is important during calculation process, and we can utilize the matrix structure to frame a particular algorithm. Even for pentadiagonal structures, if you have pentadiagonal matrix structure, then pentadiagonal matrix structure like this, that we have seen in our one of the problems or two dimensional problems, that if you have 0 values in between and you have 5 diagonals, not diagonals, one diagonal and 2 off diagonals on each side available, then we can frame our algorithms in such a way that we do not need maximum storage requirement, that is n cross n. We can reduce our storage structure by introducing different algorithms. Next lecture onwards we will start the iterative techniques to solve the same kind of problems, but the approach is somewhat different. Thank you.